Okay, we are still working with unimolecular diffusion. Previously we got the equation for concentrations. Now I want to get the partial pressures. And before we even continue, I just want to show you that this is pretty straightforward. We know that C equals PRT. So technically speaking, this is concentration factor that we have here. Also, we see that pressure repeats here, pretty similar to concentration. Remember that this is total pressure, and I have partial pressure of A in point 1 and partial pressure of A in point 2, very similar to the concentration, so you can see the analogy. Anyways, I'm going to start from 0, from scratch, so I got that NB, because it's stagnant, equals 0. Therefore, I can get rid of this, and I get this equation, which is the same equation we have been working with in the previous case. Now the interesting part is now including partial pressures. I know that the partial pressure of A divided by RT will give me the concentration of A. If this is true, I can now plug this in here. So the differential of concentration of A will be here divided by dZ, which is this part right here. And if you do some math, you can get this out because this does not depend on pressure. Anyways, remember, this is our master equation. What I'm just doing here is adding this part of the equation. Now, an interesting part right here is that we could go back. Let me go back to the previous case. We could do all these using concentrations, until eventually I will just simply plug in all the concentrations. For instance, here I think it's better if we do it. I could change this concentration and this one right here. This is always true. PART. Concentration of total will be total pressure RT. But I think it's easier if we do it already now. So I will plug it now here. I will change this in the following section. Remember that this is analogous. The partial pressure of A divided by total pressure should be equal to the concentration of A divided by total concentration. If this is true, then I get PA divided by P. And now I just need to proceed as I did before. I want to get rid of NA. I want to get it alone. 1 minus PA divided by P. Remember that you can also from now use P minus PA. I didn't do it because I want to explore further alternatives. So I remain with 1 minus PAP. What you will see is that mathematics are unskippable. You will need to eventually do so. But for now, we just keep doing this. We send the differential here, which is here, and the differential partial pressure of A. Remember that P is a constant. PA is not a constant. That's very important. Therefore, you cannot get rid of this PA here. Remember that this is constant. Temperature, ideal gas constant, diffusivity factor is also constant. So let's get away. Solve the left-hand side, which is pretty easy. C2 minus C1. And as I was telling you guys, it is not possible to integrate this. We will need to use the equation I told you, P minus PA divided by P. But because this is a division, then this goes up. So you got P over P minus PA, which is this part right here. Now you can see if you can integrate. Many times you will need to leave this as unity. So let's take it out. Thankfully, total pressure does not depend on partial pressure of A. If it would, then we could not get rid of it. Actually, we will need to use a equation depending on partial pressure of A in order to solve this. But the good thing is that we can do it. So let's take it away and solve for this integral. Remember, I don't know if you actually know, but just to get the integral of this from x1 to x2, you will get minus natural logarithm of 1 minus x2 minus ln 1 minus x1. So technically speaking, we get something like this, ln 1 minus x1 minus ln 1 minus x2, which we know using natural logarithm rules is equal to 1 minus x1. Positives remain on the top, negatives remain on the bottom, which is right here. Of course, I was using 1. If this is P, then this becomes P, 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 P. And because we're not talking about X, we're talking about P, it's partial pressure 1 and 2. So that's why 1 is on the top and 2 on the bottom. Now the interesting part right here, once again, the negative will fix this. So I just switch it. So I get rid of the negative, and once again, guys, for me it's much more natural to have a greater number than 1 on the top than a small number here. So this is typically true whenever we're talking about cases of unimolecular diffusion. And if this is true, this means that we will always take the number greater than 1. I pass this dividing and we are done. Actually, you can either leave the pressure point here, or I also like it to have it like this, PRT, so you know that's the concentration, and the diffusivity of A and B, which you know it's fixed. Oops. No, this is A1, this is A2, and the natural logarithms. Okay. Now let's work with molar fractions.